All right, so let's keep on going. So in the last video, we talked about what specific heat was, and I forgot to mention, or not to forget, but we just ran out of time. So this is your equation for specific, I'll refer to this as the specific heat equation. So it's very important to know what each of these variables mean, and then what the units are before we get into an example. So Q, we should be familiar with. Q is heat. Notice heat is going to be measured in joules. You'll see why in just a moment. M is going to stand for mass. Mass needs to be in grams. Delta T is going to be your change in temperature. And anytime you have change in temperature, it's always final minus initial. Excuse me. So you always make sure you always do final minus initial temperature, so that way you get the correct sign. And then that needs to be in Celsius. So that way when everything is put in, it's going to cancel with all of these units, right? The grams will cancel. The Celsius will cancel, and so that's how you'll end up getting your heat in joules. Once again, reminder that heat is not temperature. So I see sometimes a lot of students interchange these two variables. They're not the same thing. So make sure temperature is Celsius, heat or Q is joules. Okay, let's look at some examples. What is the amount of heat in kilojoules required to heat 255 grams of water from 25.2 degrees Celsius to 90.5? All right, so analyzing the problem, it's asking for what's the amount of heat. So that's my question mark. I'm going to make a little note to myself that it wants it in kilojoules. The mass is 255 grams. Now, it doesn't give me the specific heat of water. You notice that? But water is one you need to know. Water is the only substance you need to memorize. And actually, liquid water specific heat is different than ice water, like ice, or like water in the gas phase or steam. So only liquid water is the one you need to know. So 4.184 joules per gram degrees Celsius. That's your specific heat for water. And then delta T. Well, delta T is T final minus T initial, which I know the final and I know the initial. So we'll calculate that. And so let's go ahead and get it set up. So Q is equal to M times S times delta T. So that's the same thing as, let's just start plugging in our numbers. My mass is 255 grams. The specific heat of water is 4.184 joules per gram degrees Celsius. And then my delta T, I'm actually going to write it out. So my final temperature was 90.5. Minus my initial temperature was 25.2. So I have everything in there. Now let's go ahead and calculate. Now this problem, take a look at the math. You have two mathematical operations going on here. You're ultimately going to multiply everything, but you've got some subtraction here first that you need to take care of. So we've got two sets of sig fig rules to make sure we're watching out for. So the first thing I'm going to do, because of order of operations, I'm going to do the subtraction here. So 90.5 minus 25.2. When I do that, I end up getting, and I'm going to do it right above, the change in temperature from 90.5 to 25.2, or vice versa, I should say. It increased by 65.3 degrees Celsius. Now, one decimal place, my answer here should have one decimal place. So I'm subtracting, I need to do subtraction sig fig rules. Now, I'm going to do 255 grams times 4.184 joules per gram degrees Celsius, and then times 65.3. Now I'm multiplying, so my rules for sig figs for multiplying is lowest sig figs. 3 sig figs here, 4 sig figs here, 3 sig figs here. 3 is the lowest. So my answer is 69,700, okay, big number. Well, what's my unit? The grams canceled, the Celsius canceled, my unit is joules. So that's 69,700 joules. It wants it in kilojoules, and rightly so, because holy cow, that's a large number, right? So whether you divide by 1,000 or move the decimal 3 places, it's 69.7 kilojoules of energy. Okay, that would be the amount of heat required to do this temperature change to that water. Let's look at another example. Let's look at one more. All right, if 8,540 joules of energy is released when 927 grams of granite is cooled, it's just telling me that, sorry. If the original temperature is 46.8, what is the final temperature? Okay, let's analyze my problem here. This time I actually do know what Q is. It's 8,540 joules. Notice it's being released, so I have to write it as negative 8,540 joules. That's important. Okay, I know the mass, 927 grams. Now, it does not give me the specific heat, but I have a little table up here. So the only value you need to memorize for specific heat is water. So since it's granite, I have to give that to you. So what does it say here? 0.7953. And then it's got the units of joule per gram degrees Celsius. And then it says the initial or original temperature is 46.8 degrees Celsius. What is the final temperature? That's what I'm solving for. So I'm not solving for delta T, I'm solving for specifically what is the final temperature. So we have our equation Q equals M times S times delta T, which delta T is the same thing as writing T final minus T initial. I'm going to go ahead, before we plug in any numbers, I'm going to rewrite this equation so that way I'm having it set up to solve for T final, right? So first thing I'm going to do is I'm going to divide both sides by the product of mass and specific heat, right? So if I do that, it's going to cancel that out. So Q divided by mass and specific heat should be equal to the T final minus T initial. Then, if I just add T initial to both sides, I end up getting, and I'm going to switch my color here so it shows up a little bit better. I end up getting that T final, okay, because that's going to cancel. T final should be equal to Q divided by mass and specific heat plus initial temperature. If you didn't want to do that, if you just wanted to plug all your values in, that's fine. I don't care. But I always rearrange everything so that way it's set up for, what I want to solve for. All right, so let's go ahead and do that on this side. So equals, let me do it in a different color now so we can see everything. So what is T final going to be equal to? Well, it's going to be equal to my Q, which is negative 8,540 joules, divided by my mass, which is 927 grams. And it's also divided by my specific heat, which is 0.7953 joules per gram degrees Celsius. And then finally, plus the initial temperature. What was the initial temperature? 46.8 degrees Celsius. All right. So over here, before I do the math, the joules are going to cancel, the grams are going to cancel, and the degrees Celsius, because it's going to end up, flipping up. So, I'll end up being in degrees Celsius. So let's see. When I do negative 8,540 divided by 927 and then divided again by 0.7953, I end up getting this whole thing right here is negative 11. Let's see, a negative 11 point, I'm keeping 3 sig figs, so negative 11.6 degrees Celsius. And I'm going to add that to the 46.8, which I know was the original temperature. So plus 46.8. And now that I'm adding lowest decimal places, here's one decimal place, here's one decimal place. So my answer, when I add these two together, ends up being 35.2 degrees Celsius. That's the final temperature. Does that make sense? Well, my initial temperature was 46.8. My final temperature was lower. It was 35.2. Should that make sense? Yes, because you're cooling the granite. So the final temperature should be lower. If you did not put the negative 8,540, that's a common mistake, by the way. If you did not put negative 8,540, this would have ended up being a positive number, which means, oh my gosh, I am blowing up. I'm so popular. Which means this would have ended up being a higher value for your final temperature, like 50 something, right? And that shouldn't make any sense. Okay, if it's being cooled, your final temperature should not be higher. So that's just a little kind of common sense check, just to make sure that you did everything right. So just making sure that, if energy is being released, write it out as negative when you're doing your math. Okay? All right. We're going to do a few more examples. We're going to get to example 9, and then that'll be the remainder of this video here. So heat capacity is not the same thing as specific heat, but it's related. So heat capacity, you'll notice, is the letter C. The definition for heat capacity is it's the amount of heat required to raise the temperature of an object by 1 degree Celsius. That sounds really darn similar to specific heat, but there's a key difference. In heat capacity's definition, do you notice how mass is not included? Right? Mass is not defined as 1 gram like it was in specific heat, right? So the definition of heat capacity, which is the letter C, it's just simply saying, hey, this is the amount of heat that's required if you want to take this object and raise it by 1 degree Celsius. So specific heat, we're going to bring back some old school definitions here. Specific heat is an intensive property. It does not matter how much you have of it. It's always going to be the same as long as your substance is the same. But heat capacity, that is an extensive property, meaning it does depend on how much you have. All right, so to demonstrate that, all right, let's look at our bottle of water and our gallon of water. First question. Which has the larger specific heat, the bottle of water or the gallon of water? The question, or the answer is neither. They both have the exact same specific heat. They're both water, right? So since they're both water, their specific heat, it doesn't matter that the bottle of water is less water than the gallon of water. It doesn't matter. Specific heat for water, liquid water anyways, is 4.184 joules per gram degree Celsius. If you have 1 gram of water, it will take 4.184 joules to raise it by 1 degree Celsius. That doesn't matter if you have 1 bottle of water or 1 gallon of water. So notice that it doesn't matter how much you have. The specific heat's the same for both. Now, which one has a larger heat capacity? Meaning, which one requires more heat to raise the temperature of it by 1 degree Celsius? The bottle of water or the gallon of water? Answer is the gallon of water. The gallon of water has a larger heat capacity. It's going to take more energy to raise this gallon of water by 1 degree Celsius than it would to raise this bottle of water by 1 degree Celsius. So in this case, so heat capacity, it does matter how much mass is there. It matters how much is actually there. To demonstrate this, let's just look at an example. What is the heat capacity of 25.25 grams of lead? Okay, so what do I know about lead up here? I know lead, which is Pb. The specific heat of lead is 0.1276 joules per gram degrees Celsius. Meaning, if you had 1 gram of lead and you wanted to raise its temperature by 1 degree Celsius, okay, that temperature change, I need to add 0.1276 joules. Okay, that's the specific heat of lead. Well, I don't have 1 gram of lead. I have 25.25 grams of lead. So I'd like to know what, based on that mass, okay, because it's heavier, I want to know what's the heat capacity for this lead. So how do you solve for heat capacity? Heat capacity is just the specific heat of that substance times its mass. It's just taking the mass into consideration. So what I would do is I would, to find heat capacity, I would take the mass times specific heat. So the mass of lead is 25.25 grams, and its specific heat is 0.1276 joules per gram degrees Celsius. The grams will cancel, and so my heat capacity, let's calculate it, 25.25 times 0.1276. My heat capacity ends up being 3.222. And notice what the units are for heat capacity. It's joules per degrees Celsius. Grams were canceled out. So what does that mean? It's going to take 3.222 joules of energy to raise this particular quantity of lead to raise it by 1 degree Celsius. That's what that means. It takes that much energy to raise this 25.25 grams by 1 degree Celsius. So that's what specific heat, or excuse me, that's what heat capacity is. We got one more video for calorimetry, and it's going to be in the next one. So we'll see you then.